OK, well, my name's Ken. Thanks for coming. I'm really excited to be here in this city. I'm a software engineer at Google, and I'm a founding committer to Apache Beam. I've been working on Beam and its predecessors for a couple years now. And as the subtitle says, Apache Beam is a programming model and a library for batch and streaming big data computation. There are a number of other talks here at Flink Forward on specific aspects of Beam. This session is going to cover a bunch. My talk is sort of the high-level overview. So if you don't know what Apache Beam is, you are in the right place. And if you do know what Apache Beam is, I hope my perspective is at least entertaining to you. So I'm going to still say you're in the right place. But by the end of this talk, you should know quite clearly what it means for Apache to be a programming model for unified batch and streaming big data processing. Before you even get into it, even the outline of my talk, I just want to give this motto, which is that it's a unified programming model for expressing efficient and portable data processing pipelines. And by the end of the talk, I'm really going to have clarified what this means for you and why you should be considering Beam. So to get started, most of you certainly have some experience with data processing, but I'm still going to start by talking about big data in general terms and via a couple use cases. So just so we're on the same page about the problems that Beam's trying to address. And then I'm going to go over the Beam programming model, demonstrating how it addresses all of the use cases that I lay out. And finally, I'm going to move a bit to talking about kind of what's happening with the project, how Beam is manifesting in the world, and where we're hoping to go with it. So to set the context about the types of problems Beam aims to solve, I'm going to talk mostly in terms of streaming computations. It seems kind of appropriate for this conference, but keep in mind pretty much everything I say applies as well to batch-style computation. In Beam, there's no hard distinction. So I said it's a library for a programming model in the library for big data computation, but big data is just a buzzword, so I'm going to use this specific example, which is pretty classic. I'm going to talk about usage analytics. Supposing that we have some mobile game that's been distributed throughout the globe, and you have users playing it. You might be processing this as huge logs or as a huge stream of data as it comes. So let's focus on the streaming case. Here's your incoming massive flow of events. It's an unbounded data set. You don't expect it to have any end, at least not for the life of your game. But what else do we need to say about this data right away? Well, your users are widely distributed, so the records of the events are going to come in long after the events which the data describes, possibly out of order. So let's look closely at 3 events that happened at 8 a.m. This one we received pretty much immediately. The user was connected to a fast and reliable network. Here's another one that came in closer to 8:30. This happens for plenty of perfectly mundane reasons. Maybe they were going through a tunnel. And finally, here's an event that we found out about well into the afternoon. This, perhaps they were, they're on an airplane in airplane mode, but they couldn't put down your game because it's just that good. So delays of a second, a minute, an hour, or many hours are a fact of life. Given this distributed network of sources of late and out of order data, you want to actually compute some useful aggregation, like a user score. So what are you going to do? You're going to take the unending stream of data, and you're going to find ways to organize it into finite windows where the answer is well defined. For example, maybe you decide to compute results in fixed windows of 1 hour. So above, you see the unbounded stream of data, and below I've illustrated this partitioning into hourly windows. Perhaps this seems specific enough to give you some finite windows to compute over and reduces the problem of unbounded data to that of bounded data, which we have a pretty good idea how to do. But in fact, we need to get much more specific. Because how do you know when you have all the data for an hour? As I described a moment ago, it could show up many hours late. Or how do you decide when you have enough data to produce an actionable result? Maybe you don't really need to wait for all the data anyhow. It really depends on your application. And how much compute power, aka money, are you willing to throw at this? You may want to reduce the volume of output and redundant computation in order to save money. So I'd like to focus on 3 dimensions of customization that I just hinted at: completeness, latency, and cost. These dimensions are key when you sit down to write a streaming pipeline. Completeness means the answer you compute takes into account all the data. Sometimes we can know when we have it all, sometimes we can't, but we can get closer and closer if we're willing to wait. Latency is how long you're willing to wait before you learn something from the data. At one extreme, you might want to wait until you have all the data. You might be waiting for a while. And at the other extreme, maybe you want new information the moment any new data arrives. And it probably means the answer is very tentative and not very accurate. And it might be costly because you're going to be performing many calculations that ultimately will be thrown away. So let's look at some use cases to see where different applications come down on these dimensions. Here on the vertical axis, I've rated importance. It's a bit of a fuzzy concept, but this is going to be a crude graph anyhow. And on the horizontal axis, I have completeness, low latency, and low cost. So let's look at specific use cases, and we'll measure them against these axes. To start with, suppose we're writing a basic data processing pipeline that will do monthly billing. Completeness is critical. It's the basic spec for monthly bill that we wait until we have all of the month's data. So the blue bar for completeness is all the way up. Low latency is not important. We're not looking for sub-month results, so the red bar in the middle is very small. Note that small does not mean that we require low latency. It means low latency is not very important. So we're perfectly happy with the high latency of waiting till the end of the month. And finally, the green bar on the far right for low cost is also very small because you can't really cut corners when you're working on an accurate monthly bill. So low cost is not a priority here. But if we wanted to give users a running estimate of what their bill's going to look like at the end of the month, all of the bars change. Completeness is a bit less important. It's probably OK if we miss data for a minute and it comes in a bit later. So I shrunk the blue bar on the left. And the most important thing we've changed is that we need to get the latency down, which means that latency, low latency, becomes important. So the red bar is much larger, indicating the importance of low latency for this use case. However, we shouldn't spend a ton to make it more accurate, since it's not authoritative. And the green bar for low cost is a bit larger. Low cost is somewhat important in this case. These two use cases, you'll notice, are performing the exact same calculation. But due to their goals, they imply a different balance in these three dimensions. We really want a way to separate concerns so that we could reuse our processing logic in both cases and only have to express this balance. Now, suppose that we're attempting to identify fraud or abuse of our system. Here, we're probably using some heuristic anyway, so our computation itself introduces plenty of error. There may not be much additional accuracy gained by requiring more complete data. We probably converge on a model of fraudulent activity long before we have all the data. So the blue bar on the left for completeness is reduced even further. However, low latency is very important so that we can quickly block bogus transactions. So I've cranked the red bar in the center all the way up, indicating that low latency is our highest priority. And low cost, it's not so important. Every successful fraud detection will save us money, so we might throw more resources at the problem in order to achieve low latency. So I've talked about these trade-offs and these different use cases for big data processing, and you might think, oh, okay, what system am I going to use? This isn't anywhere near all of them. I'm not trying to be fair, accurate, comprehensive. It just illustrates how lucky we are that we have lots of choices today. Obviously, there's a bit of a bias towards Flink at this conference, but the point is that you can address many use cases and differences in performance requirements. But what system are you going to use? Well, I have two answers, which is, number one, you'll choose Beam, because it allows you to express all the different use cases using a single programming model. And my other answer is that you'll choose Beam because it allows you to run on the backend system of your choice. So let's move on to Beam itself, and you'll see why it's a great choice for all these applications. In this section, I'm going to step through each of the high-level aspects of the Beam model. At the end, you should have a sense of how the model addresses the needs that I've just brought up. At the highest level, the Beam model is going to be familiar to users of Flink, or Spark, Apex, Gearpump, Google Cloud Dataflow. In Beam, you structure your computation as a graph of transformations, which we call a pipeline. Each box here is a transform performing massively parallel computation called a p-transform. Each arrow represents the data itself being transmitted from one p-transform to the next. We call it a p-collection. Now, a p-collection does not mean a collection of data that you have sitting on disk somewhere. It can be bounded or unbounded. Bounded means we know the p-collection is finite, while unbounded means might be infinite, might be finite, we just don't know. It's easy to think of an unbounded p-collection somewhat like a stream. Now, because we recognize this convergence in these DAG-based programming models between major data processing systems, first, at Google, we open sourced the Cloud Dataflow Java SDK. And later began incubating as an Apache project. I'll talk a lot more on this later, but I want to emphasize now is how the Beam programming model is language independent and backend independent, or it aspires to be, that's what we're working towards. The vision of Beam is to allow you to write pipeline in your language of choice, like this. These boxes of code are actual Beam Java and Beam Python code. The SDK for your language translates this code into the language-independent representation of your processing pipeline. For the purposes of my slides, language-independent representation is a picture. And you take this pipeline and you run it on your back end of choice. Currently in the repository, we have runners for Flink, Spark, and Google Cloud Dataflow, which seeded the incubation process. Apache Gear Pump runner is on a development branch, and Apache Apex runner is in pull request. Runners have been proposed for other backends, such as Apache Storm. So this is the vision. We're not 100% there yet, but this is the outline that'll set the tone for going through the actual programming model, and then we'll come back to the details of how the project is progressing. So let's walk through a very specific example of Beam Java code. It's the classic word count. It's kind of the hello world of data processing. First, we use a text.io.read transform to read the works of Shakespeare from Google Cloud Storage. Then we flat map elements to split each line of input on non-alphabetic substrings. Then we filter to eliminate any empty strings we might have created before we count each of the occurrences of each of the words. And finally, we format the output and we write it to a sharded text file using text.io.write. This is a super simple pipeline. The thing to note is that it's real code, fits on a slide, and that we have not specified how to run it. Via command line arguments and programmatic configuration, you choose to run this pipeline on your laptop using our test runner, local Flink instance, Spark or Flink cluster, Google Cloud Dataflow, or any of the other runners that I mentioned, or any that come along. So when you sit down to write a program like that using Beam, you don't think about the back end, you think about 4 aspects of your computation. First, you determine what you want to compute at a very high level. If you're adding up scores for a user your mobile game, what you're going to compute is a sum. If you are working on fraud detection, you'll be computing some model of fraudulent activity. Then you think about where in event time your data is distributed. That's time as the user experienced it, and how you're interested in viewing it, such as fixed windows of an hour, or contiguous user sessions. Or maybe you aren't really processing events per se, and you're happy with having them all in one global window. That's fine too, although obviously there are some limitations to what you can do with that. And third, you think about when you want to get results. Do you want to wait until you're pretty sure you have all the data for a window? Do you want early results before the system has all the data? And then do you want to allow late results, or do you want to start ignoring results once you've emitted your answer? And finally, the fourth question is, if you are going to emit results multiple times that refine prior answers, how do those refinements relate to each other? Are they incremental sums? Are they full replacement values? So these are the things that you need to think about whether or not you use Beam. In Beam, they're separate APIs, so you can, in code, answer the questions differently. Or, sorry, separately. So we're going to walk through how these manifest in Beam in detail. So first, I'm going to talk about what you are computing. It's the basic reading, transformation, aggregation, and writing of your data. I'm going to illustrate with just one aggregation. So here's our mental model. Again, users are streaming data our way. And before we even think about how we're going to manage the data, I've already said we're going to decide we're going to do sum per user sum. So if you've, I guess, we know we want to calculate user scores. So that immediately tells us what we need to do. So here's what it looks like to do a sum per key and write it to BigQuery using the constructs of Beam. I've shown actual code in Beam, Java, and Python, but I've illustrated it over here. Those blocks coming in from the top are scores being achieved by your users, and each user is a different color. And then the sum per key groups them by color and adds them up. Right? It's simple enough to think about. It's an example of a grouping transform. You're likely familiar with it. It's one of 3 basic types of transforms in Beam. The other one that we all know about is per element transforms, which are the embarrassingly parallel foundation of your computation. It's the most powerful and lowest level is called Pardo in Beam. It's basically an extended flat map, and you can implement map and flat map and filter using these. And they're interesting because they're just as easy to implement over an infinite stream as over a static data set. And then the type we saw are grouping transformations, and they require inspection of more than one element in a P collection. So it may be per key summation or just a group by key, and they require actually getting all of the elements for one key in the same place. And finally, we want Beam to be a proper programming model which supports abstraction, so you can encapsulate any subgraph as its own composite transform to build extensible libraries or reusable transforms. Returning to the example of this grouping transformation, taking the sum per key, I want to point out that grouping transformations are particularly interesting when your data is infinite. The code on the left is not nearly enough to actually do anything with any incoming stream of data if it's unbounded. The illustration on the right is kind of an idealized mental model, but we can't actually compute the sum over an infinite collection. It doesn't actually converge most cases. So we need to choose finite windows of the collection if summation is to have any meaning. And windowing of our input into these well-defined bounded subsets is the subject of the second question. Where in event time is your input distributed? What kind of finite bounded windows make sense for you? And the question of where is all about defining at a high level these nicely organized boxes below from the stream above. If we stick with the mobile game theme and the same windowing I've been talking about, we're talking about hourly sums, so we can show maybe an hour-by-hour view of user scores. And in that case, each of these boxes below represents all the data for all the users for a single hour. Of course, recall that the data is delayed and out of order. So in order to talk about grouping the data into these windows of 1 hour, we need to talk a little bit more about time. And I do mean the topic that's been mentioned a bunch already at this conference, event time versus processing time. Here, I've drawn a completely incorrect notion of time. Each purple square represents some item of data describing an event that occurred. I drew a yellow line for event time, which is when each event occurred kind of in the real world as your user experienced it. And then I drew a blue arrow for processing time. This is kind of the wall clock as your pipeline is computing. So if networks were perfect and nothing took any time to compute, this would be accurate. But of course it's not. We don't live in that perfect world. You're going to get data at a time that's different than when it happened. So now the arrows for event time and processing time are separated. I've got event time here on the horizontal axis, and the vertical blue axis is processing time. This dashed diagonal black line is what we might call real time. It's the perfect world where I had them previously identified with each other. I've drawn some pieces of data on the line just to point out this can't really exist. All of our data lives somewhere above the line. And how far above the line it lies is the processing delay. That's how long it took us to find out about the event. Now, here's a somewhat realistic distribution of data. All the data is above the real-time line because the space below and to the right would mean we processed it before it occurred. But generally, many events, they're going to fall very close to the real-time line. But there will be outliers. So here I've identified one that's very delayed relative to the basic distribution. Let's talk about organizing these data elements into fixed windows of 1 hour. A naive way to get hourly results from this data would be spin up your pipeline, start listening to incoming data, and produce output at the end of each hour. Unfortunately, these results are not usually what you want. Each horizontal band of color here is 1 hour of processing time. But each hour of event time is marked by these vertical bars. You can see that the first hour of processing time misses some events from the first hour of event time, those two in the upper left quadrant. And there's the second hour of processing time actually includes events from both hours of event time. So there's no hour of event time corresponding to any hour of processing time. The aggregation is not based on the data, and if you want to know what a user was doing within an hour, processing time windows can't tell you. Of course, processing time is very important to us. It's time as we experience it, as we're waiting for output to be produced. But you don't have to do processing time windowing to ensure that you get output for each hour. That's a separate capability in Beam. It's called triggers, and it's going to be in a later section of this talk. An actual hours experienced by your user forms a vertical band, as I've shown here. It's just sensible. It's based on the data. Geometrically, no matter how long your processing delay is, the window in which the event occurred is the same. When we talk about windowing in Beam, we are referring to event time windowing. When you write a Beam pipeline, each element flowing through your pipeline has a timestamp attached, and the timestamp dictates the windows just like this. If you really want processing time windows, you can, of course, achieve them. All you need to do is throw away your data and throw away the timestamps on your data and replace it with the current processing time. And geometrically, it's like pushing all of your data to the right until it's on the real-time diagonal. It actually has a very clear meaning. It's transforming the event, the user scored 10 points, into the event, I found out the user scored 10 points. It's perfectly fine, but it's probably not what you want. So here's how event time windowing is expressed in the Beam programming model. It's in pretty sweet one-liners, so I can fit them on the slide. And looking at the illustration on the right, you can see that the window into transform kind of organizes this chaotic incoming data into those nice blue boxes, which are my hours. And then within each box, the sum per key operates. Writing that result to BigQuery, it's going to result in 1 row per user per hour of event time. Now, Beam ships with fixed windows, which is what I've been illustrating because it's easier to draw on a slide. It's called tumbling windows in Flink, if I recall. And I've been using those throughout. But Beam also ships with lots of common windowing strategies like sliding windows and user sessions of continuous activity. In fact, none of these are built into Beam. They're just custom windowing strategies you can write yourself. You can place elements into windows with your own custom logic. And you can merge windows with custom logic too. For example, if you have another way of defining when 2 events are part of the same session. So now we have everything we need to window this unbounded stream, right? It's not quite, because I said we'd see 1 row per user per hour, but when is that row going to appear in BigQuery? Beam has some sensible defaults, but to be totally explicit, we need to express when we want that to happen. And I'm going to bring up the same questions, which are the questions that motivate this. Do you want to wait until you have all the data for a window before you write it to a sink, to your external system? And what do you want to do when data is way late? Do you want to wait for it? And do you want to produce preliminary output? And these are all questions that are in orbit of this question of when in processing time do you want your results produced. So the answer to this is triggers, and watermarks serve your triggers by defining how complete your data is. It's kind of a deep aspect of Beam, so I'm going to go over watermarks and triggers in great detail. So recall this illustration of windowing and event time. These vertical bands of color, these event time windows, they actually extend forever upwards, right? So far, we've expressed our computations in terms of the entirety of the contents of these infinite vertical bands. We have not, in fact, managed to isolate anything finite in time or space. So how do we get something finite from this? In more sort of mundane terms, how do we deal with the fact that we can't wait forever and we can't store an infinite amount of data? Well, a naive approach would be to use a fixed delay from real time, just ignore any data that's after that. The delay being the vertical distance from the real-time line to that red line. This truncates the tops of each band, so there's a finite area, the allowed delay, between real-time and the cutoff, and it also bounds the number of concurrent windows that you're going to have to be buffering in, so it gives finite storage. It's not a terrible idea, it'll work, but it's very insensitive to your data, so you can do better. What if we could just squiggle the line and wrap it around all of our data? A curve like this is called a watermark. That straight line is really just sort of a bad watermark. We usually don't think of this as a curve. The way we usually think of it is as processing time proceeds upwards, it gives an estimate of how complete your data is in event time. That's how far we've progressed over to the right. Watermark shown here is pretty much perfect. It never cuts off any data, and yet it progresses very rapidly to the right whenever it's not waiting. So for some sources of data, such as bounded sorted logs or any where data is never out of order, we can compute a perfect or near perfect watermark. But in general, we can't predict the future, and it's going to be based on heuristic. These heuristics are actually quite effective. So late data is still a special occurrence. Let's see how a heuristic might work for this data. Here, I faded them all out to indicate the processing hasn't begun. No data has arrived, and I'm going to follow things as processing time proceeds from the bottom to the top. I've allowed processing time to advance a tiny bit, and you can see the red line is the watermark, and it hasn't advanced very far at all because it correctly estimates that we're likely to see more data in the first window. The data that's arrived are these darker purple squares. Now, I advance processing time a little bit more, and suddenly the watermark shoots to the right. That means it rapidly progressed through event time, and it correctly estimates the first window is complete. In this case, it was actually a bit slow. It would have been safe to declare the first window complete earlier. So if we say the watermark is lagging, that's what we're talking about. Now, if we fast forward just a little more, and this watermark quickly progresses all the way through the second window. Note, very little processing time has passed. The second window was processed much faster. In fact, it was processed probably too fast, because we know that there's another event in the second window that is yet to arrive. And when data arrives after the watermark, that's what we call late data. So the watermark, it gives us this notion of when windows are complete, and we can use it to guide when we want to produce output. But it's not the end of the story. If I return again to these dimensions that govern our decision of when to produce output, producing output when the watermark estimates we have all the data is great for our monthly billing example. But it doesn't address either of the other two examples. It doesn't address having a running total during the month, and it also doesn't address low latency abuse detection or alerting. So it's easy to come up with lots of examples that require lower latency. So our complete solution is triggers, which are user-written expressions that govern when to produce output. You may be able to tell that I've sort of given up on illustrating triggers really cleverly over there. Instead, I'm just going to walk through many examples, including the trigger here. And the code here, it shows a trigger that does what we've been discussing. It says you can output once the watermark estimates the window is complete. We'll compute an hourly score per user of our mobile game, and it will be written to BigQuery when the watermark estimates that we have all the data for that hour. There are no more missing pieces to this code. This is really it. Not counting the last question. Again, sensible defaults. But let's walk through how this executes, as it really will. And here's the same setup as before. The faded blocks are elements that have not yet arrived. The Java name for the trigger is after watermark past end of window, but that's Java. After some processing time passes, the watermark estimates the first window is complete, so we output an aggregation for that window, which includes just the single element. See, we can see the future, and we know that another element is going to arrive, but the watermark doesn't know about that. Now, processing has continued until the watermarks declared the second window to be complete. So output was produced for the second window. In addition, the additional element in the first window showed up by now, but it was too late to be included, so it was dropped. This allowed lateness when you drop data is configurable, but just to be simple for now, I've left it at 0. So stepping back and looking at the entirety of this execution, we can understand that this trigger is high completeness, potentially high latency trigger. It waits about as long as you can before producing output. So the volume of output is about as small as it can get, and likewise the redundant processing. So it's generally a low-cost trigger as well. It doesn't matter if you get 1 element or a billion, it's only going to output 1 aggregation. Let's turn to triggers that trade off completeness for lower latency. This trigger here, repeatedly forever, after pane element count at least 2, it's ready to produce output whenever at least 2 elements have arrived. In practice, you'd use a much higher number, but for slides I've chosen 2. It's totally independent of the watermark. It just ensures once we've got some data, we'll produce some output. So after a bit of processing time, 2 elements arrive in the second window, and we immediately emit an aggregation for the second window. This element in the first window is waiting for a second one to arrive. Note that the watermark's barely advanced at all. It doesn't actually matter because this trigger does not depend on the watermark. Now a bit more time has passed, but the watermark has still barely advanced. We have 2 elements in the first window, so their aggregated output is produced. Note the outputs for the windows are produced out of order. Windowing and triggering does not sort your data. And progressing a bit more, 2 more elements arrive, and another aggregation is produced for the second window that accounts for all 4 elements. Looking at the entirety of this execution, it's an illustration of trading completeness for latency and cost. Trigger ignores the watermark, so it's not appropriate when you need completeness. The latency is determined by input. If there's a constant onslaught of input, output will be produced very quickly and will always be up to date. But the cost could be much higher, precisely because there's so much more data being processed downstream. These prior 2 examples were basic building blocks, but Beam includes combinators. Here, I have a trigger where the base case is after watermarks pass the end of window. It's like the authoritative monthly billing use case. In practice, you probably want to wait a little bit longer. But then I've also added early firings after the processing time is 1 minute past the first element that arrives. This can provide us a running total for a monthly bill with updates throttled to 1 minute and latency also approximately 1 minute. And we've also specified late firings after a single element has arrived. So this does immediate corrections to your bill if we do find out about an additional transaction. Let's see how this evolves focusing on just a single window. Initially, 2 elements arrived and they're buffered. The watermarks hardly moved at all and we're just waiting. 1 minute after these 2 elements arrive, 1 processing time minute, we emit an aggregation. Pausing here for a second, this has some really nice properties. You're never sitting on knowledge indefinitely without producing output, and yet it can be a lower cost way to reduce latency because since output production is bounded per unit of time. Moving along, the watermark now concludes that the window is complete, and so we emit an on-time output. This is specially labeled as on time so that your downstream stuff can know that it is the authoritative output. This would be your monthly bill. And then time passes, long after the watermark said this window is complete, a late element comes in, we immediately produce a revised output. This trigger is a prime example of how you can use Beam's language of triggers to assemble a trigger that's right for your application. So those are just a few examples. Beam has a rich catalog of triggers. I'm not going to go over all the stuff on the slide here. I'm just throwing it up to say there are many choices, and you should go to the web page because slides get out of date anyhow. And you really can express a very wide variety of behaviors. OK, so finally, if you do decide to produce output multiple times for the same window, you can choose how these outputs relate. In particular, you can choose whether they represent only the incremental aggregation since last time or the complete aggregation that should replace the one before. Let's look at these two accumulation modes quickly just by watching how our results evolve. On the top, we have discarding mode, and on the bottom, we have accumulating mode. So after some time, we emit the output 5. So far, so good. Now, if the next triggering occurs after another 2 is added, well, in discarding mode, we have discarded this 5, and we just emit the delta of 2, while in accumulating mode, we emit 5 plus 2, which is 7, and so on. As more data comes in, causing additional trigger firing, here in discarding mode, we emit 7, while in accumulating mode, we emit the total sum of 14. And again, the delta is 11, and the total is 25. This is which one of these you need is going to depend on the characteristics of the rest of your pipeline. So if you remember one thing about the Beam model, remember these questions. Even if you don't end up using Beam, I assert that you're going to have to answer them. And the great thing about Beam, as I mentioned before, is that we have separate APIs for these independent questions. OK, and now we'll move on to Beam the project. Beam as a project specifically refers to the Apache project. We've got Apache Bug Tracker, Apache mailing lists. I'm still very excited about it because I'm new to working with Apache. And we've got a web page and GitHub pull requests. So let's get into the details of the project's life. I'll start with a tiny bit of history and move on sort of the project's vision and where we want to take it. So from the beginning with Cloud Dataflow, we had an open source SDK representing the programming model and hooks for other runners. And it sort of worked. Cloudera made a runner. Data Artisans made a runner. But kicking code over the wall from Google is not real collaboration. It's not enough to build a community, and it's not as ambitious as Beam, what Beam represents now. So we got all three donated to a single code base to jumpstart the Apache incubation process, and now they all live together and share tests and everything. And importantly, all the runners are on equal footing, part of Beam, which is governed by Apache. We have a diverse set of founding members from Google, Data Artisans, Cloudera, Talon, PayPal, and people with GitHub badges from lots of other notable organizations. Our broader vision, beyond just runner independence, I mentioned language independence, and this is, we think about language and runner independence by talking about three groups of users. End users, which are the stick figures that they want to write pipelines in their language of choice. SDK authors make that possible by implementing one side of the Beam APIs and translating the Beam concepts into a particular language, and runner authors, like the authors of Flink, Google Cloud Dataflow, and Spark, that have a distributed processing backend. It's the vision, so where are we? Well, this diagram sort of shows the history and where we're going. We have Dataflow 1, and in February, we forked it, and we started making crazy breaking changes, just getting all the runners working really well together, adding new runners and new SDKs. We've had a couple incubating releases. When we're ready to guarantee backwards compatibility for a while, we'll make a stable release. I want to emphasize that actually Google does their new development in Beam, and we backport little bits to Dataflow. But Beam is where primary new feature development goes. So for programming model as rich as Beam, we don't require all the runners to support all the features. Otherwise, it would just sort of be the lowest common denominator. Instead, we keep these capability matrices on the website, so you can see which runners support which features. It changes frequently. This is probably already out of date. So you should go to the website and check it out. And for example, the Flink runner now supports side inputs in streaming mode. I'm going to skip these because I'm running out of time and I want to get to questions. But I do want to just show you these quotes, which I really find inspiring, from Tyler at Google. We don't want lock-in. We want these runners to all be competing on this new playing field, which is Beam. And from Kostas, this lovely compliment that the Beam model is a great programming model. So these make me really want to work hard on Beam. That's it. I hope you enjoyed this one. this overview, and I definitely hope you stick around to see the next 2 talks on Beam from Malo and Max. And that's it. Please visit the Beam website. Please join our mailing lists. And if you want to dig deeper into perspectives on the Beam model, you can read the Streaming 101 and 102 essays by Tyler, and certainly read the Why Apache Beam blog post from DataSins and Google. Thanks. I see questions over in the back there. Where's where the hand shot up?
So thanks for the nice talk. If I understand correctly, for these 4 highlighted questions, you provide kind of somewhat loosely coupled APIs and kind of sublanguages to express the answers for these 4 questions. And so my question is, what is the restrictions, what is your data model that ties together these 4 languages? So, and to bring a connection, for example, with Spark, which started with an untyped data model with the RDDs, and now kind of slowly figures out that kind of knowing semantics of the underlying data elements being processed allows to compute and execute more efficient code. So do you have any thoughts in the same direction? So what would be kind of the element?
We've had thoughts in that direction. If I understand your question correctly, so the data model is we have these P collections, and the data elements in them are just encoded to byte arrays. So in that sense, it's an untyped data model. And I am familiar with the work in Spark where having kind of explicit data structures that the runtime understands could speed things up. There's nothing like that in Beam today, but I do think it's an interesting idea.
Hello. I would like to ask, when you showed about the late firings,
okay,
you didn't specify anything about allowed lateness. This means that or
Yep. Yeah, you got me. If you don't set the allowed lateness to be greater than 0, it will drop everything.
Okay. I was wondering if you keep forever the same window and you keep on refiring if you have this option. But no, I suppose there is a horizon.
There is. And you do need to set the allowed lateness to a non-zero value or one. Yeah.
Hello. So thanks for the talk. One question, is it possible to use Apache Beam as a kind of benchmark for the different run implementations? So let's say I have some kind of computation I want to carry out, and I do it once with a Flink as a runner and once with a Spark. And it runs better with Flink. Would that mean that Flink is better adapted to my data processing, or is it just that, for instance, could it be that the runner is implemented in a better way than the one for Spark?
I think that the answer is yes and no, which is that you can write a pipeline in Beam, and in some sense you have a very specific definition of a pipeline, which then each runner may have different performance characteristics on. I wouldn't say that that necessarily reflects directly on the backends, because writing it in their sort of native dialect, you may get different results.
Right.
So I would say that that is a necessary thing to measure, which is how do Beam pipelines run on each of the different runners. But Beam introduces some abstraction and some overhead in places.
Okay, thanks.
There's a couple up front.
Hi. The question I had was something along the lines of the previous question. Say, for instance, some of the features that are exposed by Beam are available in only one of the runners. Say, Flink has those features and they are not supported in another runner.
Okay.
Can I just plug in multiple runners and say if, for instance, for a stateless computation, I may want to run on a runner A, and then for a different one, I can choose runner B. Is that possible? I
Yeah.
mean, have multiple runners
It's very
in right away.
Yeah, absolutely. It's very easy. It's actually, you can download Beam today and do that with our examples. You -- runner equals Flink runner.
But would that be changed dynamically, depending upon, can I set rules, as in, if
Well,
this condition's met, I want you to use runner A.
Yes. Yes, you can definitely set it dynamically. The command line option is just shorthand. In general, you would be launching it from a program, right? You launch your pipelines from like your Java main that's interacting with the Beam Java SDK. And so you have whatever logic you want to have there, and you can set up the runner then. Does that make sense?
Yeah.
Yeah. Okay.
Hi, thanks. Just a question. When will the Scala API be released?
Well, so the Java SDK runs on the JVM. You can just use it. No.
We're
So
fans of Scala. So
Yeah, I love Scala myself, and it's unclear. So SDK we tend to refer to sort of the nuts and bolts of making it available to an additional platform. And so for Scala, we might call it like a DSL, like having some friendly Scala-ish ways of interacting. You don't need to do as much work as you do to actually build an SDK. So that would be probably a slightly easier or different sort of project. There's actually one out there in the wild, which I don't know if you've heard of Scio, SCIO. It was built on the Dataflow SDK.
from Spotify? Or,
Yeah. And it's awesome. And we certainly want to get that ported over to Beam. But of course, right now, Beam is kind of a moving target. So anybody who has kind of, I don't know, the fortitude to stick with us is welcome to try that. But yeah, we certainly do encourage DSLs like that. And I should say we encourage getting them contributed to the repository so that we never break them because they're sharing our tests, and if we break them, then we have to fix it. Okay, well, thanks.